Okay, so let's start the lecture. So welcome, this is week 3, and it's our second lecture, and this is one of the, I think, most fundamental elements of the course. Our opportunity to discuss power delivery, clocks, resets. These are all fundamental things that apply to microprocessor designs, microcontroller designs that are key to embedded system hardware. So I'm looking forward to the topics. Before we get into those details, the TAs have now published their initial office hours. Hopefully you saw the email from them. Did everybody get that email from the TA?
Yes.
Great. So what we did is we took a look at the feedback we received from homework 1, tried to choose time slots which met as many of your interested time slots as possible, and we'll take it from there. If we find that you're not able to attend or we have a few time slots that aren't well used, then we'll make some changes as we go through the semester. Today we'll talk about power integrity, decoupling capacitors, power delivery. We'll talk about the elements that we use to distribute voltage to our silicon, which will be our voltage regulation system. We'll talk briefly about heat sinks. Crystals and oscillators are timing sources for our hardware, and then briefly about supervisory circuits, and then we'll see how much time is left. A quick review, we won't touch on all of these right now, but you can look at the notes later. This week we've got software elements of Lab 1 due, and hopefully you've all been able to make some good progress on that. What the TAs will do for each lab assignment is publish sometimes for sign-off slots, and you will sign up for a sign-off slot which makes sense to you. The TAs will have just a limited number of people in the lab during the sign-off, and you need to come to that sign-off prepared. So in addition to have completed your work, you should review it, make sure that all the aspects of the lab are very familiar to you and that you can explain what you've done and the significance of that. And be prepared for the TA to ask you a few questions about the material and to probe your understanding a little bit. It can be a dialogue if you have a little bit of time and you want to mention something you've learned or something you saw during your lab development time that confused you or was suspicious. You could bring that up during this, but the primary reason for the sign-off is to make sure that you've completed all the elements and that we've evaluated your skill at that material. The topic next week will be finishing any leftover material that's relevant for Lab 2. And then we are going to talk a little bit tonight about technology topics and what we might do about presentations later this semester. What I've been doing over the past few semesters is something called a current topics presentation. And we can make modifications each semester to this, but it's an opportunity for us to explore topics which might be of interest to you and which you might have work experience in. So if you have worked in industry on a particular technology topic, it might be interesting for you to share a little bit of your experience in a classroom setting. The types of topics that we've covered in the past are shown on this list. We've covered some specific aspects around ARM architecture and ARM system development, battery technologies, battery management, fuel gauges, things that you use in an embedded system to determine how much battery capacity is left and how you might make modifications to your runtime settings to maximize battery life. Sensors tend to be very interesting to students. And then, as you can see this list, lots of different areas relative to the embedded system domain. I guess I'd start just by saying, for those students in the class, have any of you worked professionally in industry in the embedded systems world? And can you already think of a topic on this slide that you might be interested in presenting? I just curious as to whether somebody had that experience that they would be interested in sharing. Okay, I don't see any hands yet. We will come back to this again as we go through the next couple of weeks. But if there's something here that sparks your interest and is something that you would like to explore more, let's have that conversation, because there may be an opportunity for you to spend a little bit of time doing some research on these areas this semester. The other thing on the list that I'd like to point out is that I do an honor code quiz. This is a very easy quiz, and you'll all get 100% on it, but I do want you to plan to do that over the next couple of weeks. This is a quiz that I'll post on D2L for you to complete, and you can take it as many times as you need to get the 100%, but it shouldn't take very long. It's important, though, because I believe that the honor code is an important part of our educational environment, and I want you to understand it completely. All right, let's move into our technical discussion. Power delivery is a critical element of hardware design. It's something that requires good understanding of how all of the different pieces of the system interoperate and how they can impact each other. It has a lot of different types of impacts on system design. You, of course, need power to all your chips to make them functional, but how much does it cost to get that power to those chips? How much thermal challenge do you have in your system design when you're dissipating heat in your regulators and your heat sinks need to be designed in a way that complies with the form factor or industrial design for your product? Those are all things that are sometimes very tricky to accomplish. If you are designing an embedded system that has to dissipate a lot of thermal energy in a very small environment, the expertise that's required can be significant. So we'll touch upon the thermal concepts briefly tonight, but our primary focus is going to be on understanding the electrical aspects of designing a power delivery network. Okay, first off, I'd like to just get an idea. How many people have studied decoupling capacitors in depth? Okay, we'll spend a few minutes talking about this topic. It's a really important topic. When I take a look at the system designs and board designs that I've covered in my career in industry, decoupling capacitance is one of those really critical and fundamental things that you need to think about up front. It's not something that you go back and try to add in later on. Let's talk about the decoupling capacitor and some of the considerations that you need to make. On the left-hand side of this screen, I have a simple network. I have a power supply, maybe a battery, or a DC voltage. I've got some type of circuit wiring. Maybe it's a printed circuit board, maybe it's cabling, maybe it's some combination of those things that give me a path for current to flow from our power source through the load circuit and then through a return path back to the power supply. As you can see in this diagram, the path that current flows is modeled with a line impedance. So you can see that there's inductance and resistance shown on this diagram. Anytime we have current flowing in our system, we have these two elements which are impacting our ability to get charge from the voltage source to the load circuit in a way that it's needed quickly. What we see underneath this is a diagram of current, and these current spikes are representing what happens in your load circuit. If you have a bunch of integrated circuits or motors or anything else that's drawing current, the amount of current that those load circuits draw over time is not constant. They will be transitioning, outputs will be changing state, and every time you go through those transitions, it causes a change in the amount of current that has to flow through your power delivery circuit. And when you get these bursts of current, you get an impact on your voltage rail. And what you see in the bottom diagram are these perturbations or deltas that occur on the VCC rail because you're taking these large draws of current over a short period of time. The equation that we're taught in our theory classes that relates the size of those voltage excursions to the circuitry is this equation at the bottom of the screen, where we know V equals LdI dt. What we're talking about here is a delta V, or the size of the variance that you have on your VCC lines. First question is why is delta V important to us? Why does it matter how large of a noise you have on your VCC lines? Can anybody comment on that? Yes, in the front.
Yeah, so some devices that have any VCC requirement will shut down if they're not getting enough power.
So one comment is if they're not getting enough power, but another piece of that is if your voltage delivery is not staying within the specifications of your integrated circuits, then your integrated circuit is not going to perform the way the datasheet says it's going to. And how it chooses or how it does not perform according to the datasheet, you may not be able to anticipate. It may still work, but may have varying characteristics, or it just may not function properly at all. So our job as hardware designers at this point is to make sure that we understand what the manufacturer of the silicon specifies as a requirement is met in our design. If we cannot do that, then we're not delivering a robust hardware platform that you can rely on as a product. So first step, understand what the requirement is. Second step, make sure that we meet the requirement in how we design our circuitry. In this particular case, we see these graphically pretty large delta V's superimposed on our VCC rail, and we can imagine, hey, wait a second, that looks significant. It's very possible that I'm getting a voltage drop because of that current spike that's causing VCC to go down below the minimum value of VCC temporarily. And if I do that on certain types of chips, especially processors, the processor has lost control and the state machine that's governing its function is not necessarily where it should be. Our job is to try to maintain control over that state machine at all times, and we do that by giving the processor a clean voltage supply.
I don't understand. V series is graphically pretty large delta V superimposed on our VC series now, and we can imagine, hey, wait a second, looks.
I have a phone next to me. Siri was listening to my conversation, and she was trying to respond, talking about delta V and everything. Okay. So what we see on the circuit on the right is we've added in a circuit element, this decoupling capacitor. And what this capacitor is doing is it's providing a local reservoir or charge point of charge close to the load circuit so that when the load circuit changes state, the capacitor can deliver charge quickly to the load circuit and not have to wait for that large current spike to propagate through the transmission lines from the power source. What you see in the diagrams or figures down below, you still see the same types of current spikes that you saw in our first example on the left, but this time what we see are these smaller deviations on VCC. And depending on what we've chosen for our decoupling capacitor and where we've placed it in our circuit, we can influence the size of that excursion on VCC. There are some processors or some chips which have very, very tight requirements on VCC. I've worked on microprocessor systems that make you require you to control the supply voltage to within a few millivolts. And doing that when your processor could be drawing tens or hundreds of amps of current can be a really challenging part of your design. Luckily, what we're going to be exposed to in the first part of the semester is nowhere near that challenging. Our 8051 variant is not as demanding in terms of its VCC requirements, and we'll be able to clean up our voltage rail enough to satisfy the 8051 requirements without extreme difficulty. However, the more advanced processes that you use, the more low voltage processors that you choose to use in your embedded systems, the more this becomes an issue and the closer you have to pay attention to this part of the design. If you take a look at this equation at the bottom, delta V equals L di dt, you have a couple of different pieces which influence the delta V term. The first is the di dt. So how much current is being drawn by the load circuit and how quickly is that circuit being drawn or for how long. The other piece is the L term, the inductance term. And if you recall inductance is majorly influenced by what? What geometric characteristic? Loop area. So the larger the loop area in our current flow from source to destination and back to source, the larger the inductance, and therefore the larger the L term in this equation. If I can find a way to reduce the L term, even for the same di dt, I'm going to reduce the delta V in this equation. And that's exactly what that decoupling capacitor does in the right circuit. Instead of looking at this entire loop here on the left, I'm now able to take a look at quick power delivery in this little loop on the right. And that's reduced my L term significantly. This implies that not only does the existence of the capacitor matter, but the location of the capacitance matters. If I put that capacitor far away from my load circuit, I have not done a good job at reducing that loop area, and therefore it's not going to do as good of a job at reducing my delta V, or the voltage excursion on the VCC line. If I can put the capacitor very close to the load circuit, I keep that loop area small and the capacitor is more efficient. There are some other factors which influence how well that capacitor functions. For instance, the capacity matters. If I've chosen a capacitor which is very tiny, it's not going to be able to store enough charge to handle a very large change in current draw from that load circuit. So I also need to consider how much charge reservoir I provide there and choose something that's large enough to handle the spikes that are seen. In your homework assignment, I've given you some reading. I asked you to read an application note that talks about power delivery, and I think it's an important one. So I'm hoping that you've read it, and if you haven't yet, please do so. In this simple diagram, we're taking a look at a few chips that are on a circuit board. And these chips are connected to our power and ground planes or rails or traces so that the chips can get their power supply. And on the top diagram, I can see that the way I've connected the power pin and the ground pin of this logic IC, I have a relatively large loop area, and the capacitor is located kind of far away from the chip. In the second diagram at the bottom, I've improved placement a little bit. In this case, I've kept my VCC and power or ground traces or wiring underneath the chip, closer together, and I've put the capacitor tying ground and power together closer to the chips. This decreased area of loop on the bottom implementation will give me improved circuit performance, even if I've chosen the exact same type of capacitor as I did in the first design. So when you're designing your circuit for the class this semester or for any embedded hardware design that you want to do after this class, not only should you reserve space for decoupling capacitors, but you also want to make sure that as you place those components on the board, you're thinking through, okay, what chips does this capacitor need to help? And place the capacitor close to those chips. This scope shot is a little bit hard to see, but I'll describe what you're seeing. What I have here is a series of scope shots, which show what happens to noise on our VCC line connected to the power pin of our 8051 processor. And pin 40 is the VCC pin. ALE is the address latch enable signal, which is an important signal in the 8051 architecture. And that signal transitions, and when it transitions, it necessarily causes significant changes to load circuit current because other chips connected to that control signal draw or stop drawing current on the edges of that signal. What you see on the pin 40 diagram is that the VCC rail changes quite a bit, and the two blue horizontal lines here and here are showing you the top and bottom of the excursion that you see on the VCC rail. On the right scope shot, I've improved the situation some, and that's just by adding a 0.1 microfarad decoupling capacitor on the printed circuit board that is helping to reduce the loop area and provide that local charge storage to deliver to the load circuits when they switch. And you can see that the this distance between the top and bottom blue lines has decreased significantly in this case. I now take a look at two other experiments after this. And instead of having the 0.1 microfarad capacitor just on top of the printed circuit board, I've now taken that 0.1 microfarad decoupler and stretched it directly between the power and ground pins underneath the socket for the 8051. And as you can see, I've got some increased performance. Again, I'm a tighter on my VCC rail, and it's not as much of an excursion. On the right side, I've now have the same physical location of that capacitor, but I've increased it from 0.1 microfarads to 1 microfarads. It's improved the 1 megahertz ripple that was present in the current, but other improvement in high frequency components really isn't there. So I've done a pretty good job of stabilizing my VCC line with a certain amount of noise. The last experiment that was tried on this particular design was to use a special construction of the capacitor. And this decoupling capacitor happened to be the same general shape as the integrated circuit and could be placed directly underneath the processor chip. And again, we've further decreased the magnitude of the excursion seen on the VCC line. What does this mean to us? It means that we've done a better job at providing cleaner power to the chips, and therefore they will perform better than if I had provided dirty power that was allowing the chip to operate closer to its minimum or maximum voltage levels as determined or specified in the datasheet. This is another application note from TI, and the source is listed at the bottom of the slide if you want to look at it on the website. But this is also showing some experiments where they take a decoupling capacitor, shown here on the left of the diagram, and apply it to a circuit which is basically just got a simple gate that's switching and feeding a load at 50 milliamps of current draw. And this is some of the data that they got from that experiment. On the top left side, you can see that the distance of that capacitor from the VCC pin is listed at 0.3 inches. So there's a capacitor 0.3 inches away from the VCC pin, and the diagram shows you a range of voltages seen on the VCC line for each size capacitor that was tested. So if I start here on the left side of the diagram, you can see a 0.001 microfarad capacitor was used. And I have a medium large voltage excursion on the VCC rail. I then move across this diagram, and you can see that as I've increased the size of the capacitor, the magnitude of that voltage differential has now reduced, and I've cleaned up that voltage rail some. I get over here to the right and I see, it looks like it increased a little bit. I'm not sure exactly what happened there. There are a few things that can impact the quality or the performance of your decoupling capacitance. And one of them is the package technology that is used on your decoupling capacitor. For instance, if I use a capacitor with through-hole leads, so leads that go down through the circuit board and get soldered in, those will typically perform worse than a capacitor which is a surface mount capacitor and can be soldered directly onto the board. The reason for this is that the capacitor with the leads that have to be soldered through the board will necessarily have additional loop area as a function of the current having to go up the lead into the capacitor, down the lead to get out of the capacitor. If I use a surface mount chip, I have removed that additional path for the current to flow, and the surface mount capacitor will give me a lower inductance for the same capacitance size. The other thing that can influence what I read with a scope probe is resonance effects. So if I have chosen capacitors that have a particular capacitance, inductance, resistance, and they interact with a circuit in a certain way, you can get results which will show you maybe greater noise than what you were hoping for. One thing I want you to all recognize is that when we talk about components, especially maybe these passive components, capacitors, resistors, inductances, or inductors, the component is called that, a capacitor, resistor, or inductor, but it has the properties of all three of those. So a capacitor that I put in the circuit is not just a pure capacitor. There are inductance impacts, there are resistive impacts. And for particular uses of those components, we have to be aware of those other characteristics, not just the pure capacitance. The lead inductance and the effective series resistance of a capacitor can influence how well it performs in a power delivery system. The diagram on the right shows performance of the decoupling capacitor as you move it further away from the VCC pin. In this scope or set of data, the capacitor now has effectively increased the loop area because of its placement. It's further away, and we see generally worse performance at a particular capacitor size. And then as we further increase the distance from the load circuit, I get increased perturbances on the VCC rails. The lesson that you take away from this is when placing capacitors for decoupling, try to place them very closely to the load circuits that they're decoupling. Every single integrated circuit that you're going to add onto your board this semester should have a bypass capacitor added to the board as well. The 8051 processor that you have put on for Lab 1 will probably be one of the largest current draws of any chip that you put on. It has a large number of outputs that it switches simultaneously, and therefore the decoupling capacitance that you provide to that chip, the 8051 chip, has to be larger than the decoupling capacitor that's needed for many of the other chips that you put on the board. So how do you go through the process of calculating capacitor size used for decoupling? The application notes that I've assigned for your reading talk about this a little bit. One of the application notes mentions that there's some general rules of thumb that people might apply. And for TTL circuits or this type of simple combinational logic, somebody might choose to include a 0.1 or 0.01 microfarad capacitor for each chip, just to provide some local decoupling. But the application note also talks about larger capacitors called bulk capacitors. Has anybody read the application note yet and can talk about what this is? Okay, so a bulk decoupling capacitor is basically a larger reservoir of charge. It has a larger capacitance value. It may not be as fast to respond to changes in the load circuit, but it's faster to respond than the original wall adapter or power source that you're using for your embedded system. And what happens in the design is that you can set these capacitors up on your board in such a way that there are high frequency capacitors near each chip, and then there's these bulk decoupling capacitors which may be located further away from the chips, maybe close to the voltage regulator or power supply, and they work together as kind of a bucket brigade. If people are familiar with the concept of a bucket brigade in fighting fires, you might recall that a line of people pass a bucket or pass water from one bucket to the next down the line until it gets to the end. And having bulk decoupling capacitors in concert with high speed or high frequency decoupling capacitors can work the same way. The bulk decoupling capacitors get refilled from the main power source, and they provide a local but not really close availability of charge. And then the little decoupling capacitors provide smaller buckets of charge that are quick to deliver to the chips. So if a chip has a line that transitions and requires a quick burst of current, the current can be, or charge can be supplied by that local decoupling capacitor, and then it can refill by the bulk decoupling capacitor, which provides charge to replenish the smaller high frequency capacitor. So charge kind of gets passed along to the destination, but it's done in such a way that the amount of noise seen on the VCC line is minimized. It's very low amount of noise. So the application note talks about a couple of ways that you might approach calculating the capacitance sizes rather than just using this rule of thumb, because rules of thumb don't always apply. They're just a starting point. There are going to be some chips that you put in your design which exceed the requirements of a 0.01 or 0.1 microfarad capacitor. And how do you know that? Well, this slide shows you one of those ways. And what this example is showing you is that if you know how much current is being drawn from your load, maximum, you can start to calculate the capacity required from your decoupling capacitor. And the basic equation that we keep in mind as we go through this process is that Q equals CV, and that if you rearrange that, C equals Q divided by V. So if we know how much total charge, and V being the delta V, how much voltage change we can accommodate on our VCC line, you can calculate the amount of capacitance that's needed to provide that electrically. So in this example, the letter I represents how much current's needed for one output to switch from low to high. When it switches from low to high, a large boost of current is needed to charge up the line capacitance and get it up to the high voltage level. The number of outputs switching simultaneously is N, and the time required for the capacitor to charge the line is delta T. Basically, how much time does it take for that chip to switch its output from low to high? That's how much time you have to provide charge from the decoupling capacitor. And then delta V is the allowable or acceptable drop in VCC that you're willing to accommodate. And if you know those values and you plug them into the equation here, you're able to calculate a capacitor value. So if you take a look at this equation on the left blue box, you can see it's basically the same form as the equation in the right box, where I times N times delta T gives you an amount of charge, and then you divide that by the delta V, which is the acceptable change in your VCC rail, and that gives you a calculation for capacitance. In this example, they worked it out to calculate a decoupling capacitance value of 0.01 microfarads. Okay, so the first question I have for you is, as system designers, if you had this scenario and you calculated you went through this calculation, what capacitor do you put in your system? How many people put in a 0.01 microfarad capacitor? Nobody. Okay. Do you put a capacitor in at all?
Yes.
Okay. So what are you going to choose?
I guess
Something more than that, yeah.
0.01.
More than that, right. And why is that?
Because you're trying to-
Capacitances have tolerance.
You're trying to have margin. And the fact that capacitors and other components have tolerances associated with them, and they change characteristics because of temperature, and they change characteristics because of aging, and you want to make sure that you've designed in to accommodate this margin. You don't want to just put in a circuit element that's exactly equal to this calculation. You've lost any margin that you might have wanted. So this gives you a boundary, and then you make the choice. Okay, it calculated 0.01. I feel comfortable I could put in a 0.1 microfarad capacitor, and that would be plenty to accommodate this load. Yes, and then
is there a way to calculate the other boundary, like when the capacitor response becomes a concern? Like if you're doing too large of a capacitor, then it's not going to be able to respond.
Well, the question is why would too large of a capacitance impact the circuit? And one of those things is if you've changed package size. So if the choice of a larger capacitor means that you have to go to a larger package size to get that amount of capacitance, you now have a flag, a red flag or a yellow flag that kind of warns you, hey, wait a second, I need to think carefully about this decision because I'm introducing something that probably has a larger inductance than what I could have gotten away with a smaller capacitor. So that's the kind of the first gut check that you would have. Another thing that you could do is measure in your circuit. This is something I haven't gotten to yet, but one thing that sometimes system designers will do is they will put placeholders in their circuit. They may say, I need decoupling capacitance in my circuit, but I'm not sure exactly how much. And so what they do is in the design, they put a whole bunch of capacitors and they put them close to each chip where it's needed. And then once they get their prototype boards back, then they optimize their circuit based on actual functionality. And there are at least a couple of different ways that people approach this. One is that they start with all those capacitors populated in their board, and then they test it and keep removing capacitors until they get to a point where the system starts to fail or is at a marginal level. Another way people do it is they start with no capacitors on the board, and then they start adding capacitors to it until they get to the point where it passes. And each of these approaches is done at least in part to try to optimize design cost. They don't want to put extra capacitors on a board if not necessary, because it adds the cost of the capacitor and it adds the cost of adding that capacitor to the board in production. It's not just the BOM cost or bill of materials cost of the pure component that you buy. It's the cost in manufacturing of taking that component, putting it in a feeder that goes into a pick and place machine, putting it on the board, and then potentially dealing with yield issues because the part didn't get soldered correctly. All of those things can add cost to the design that you may not want to have there. And so in practice, before you go to production, you try to optimize your design to eliminate unnecessary components for those reasons. Now, another way that you can go about calculating capacitor size is by dealing with this specification of slew rate. And it talks about a spec that you might find in the spec sheet. And I'm not going to go through this, but I will point you to this application note where it does talk about this a little bit more. The main point that I want to get across to you is, number one, the importance of decoupling capacitors and the fact that you shouldn't be ignoring them. And then two, if you're going to use decoupling capacitors, what the correct way to approach your design should be. And that is making sure that you've chosen good placements for them and you've considered the impact of package sizes and component characteristics in your choice. If you were designing a capacitor which needed to provide bursts of current in a very, very short amount of time, your consideration of the inductance and ESR and ESL characteristics of that package could matter. You would want to understand, well, if I'm doing burst current from, or burst charge delivery from that capacitor to my integrated circuit, and it's coming through the leads of this capacitor, and that capacitor has effective series resistance that is significant, I'm actually going to get some voltage drop between the capacitor voltage and the pin of the chip that I'm delivering to. And in addition, I'm going to get some heat loss. What is the power associated with the current that's flowing through that effective series resistance? It's I squared R. We know that from Ohm's law, the voltage drop is IR, and then that times the current of I gives us I squared R losses that are in the capacitor itself. And if you have a capacitor which is working very hard, which it does maybe in a switching regulator circuit, those ESR and ESL components can influence how hot that component runs and whether it maybe fails early because of the thermal load. Okay, before I go into voltage regulators, I'll pause. So if you've designed hardware before, have you added decoupling capacitors to your designs, or is this a new concept to you?
New concept.
Okay, so think about this as you go through the lab assignments. It's actually one of the checklist items on our labs this semester. Did the student add decoupling capacitors? So if you just think up front, okay, every time I add something on, I should be thinking about adding some decoupling capacitance, you'll be in good shape. But if you're going to be optimizing a printed circuit board for a product, you'll need to take it to the next level beyond where we get in this class. You'll have to analyze it to greater detail. Yes, front row.
Most like microcontroller data sheets tell you what capacitors to add to what slide pins of the chip.
I heard part of that, but
oh, sorry. Yeah, I mumbled. It seems like most data sheets for microcontrollers tell you exactly what capacitors to add and where to add them if you want them to behave properly. So.
Yeah, there's a good number of chips that do that these days. Not every chip has as good of a support or technical documentation as others, but if the data sheet doesn't show it, oftentimes there's an application note that the company provides which says here's a reference design, and for this reference design I've added in this capacitance. But not all chips will give you that, and once you start putting multiple chips together, then it becomes a little bit murkier because maybe you don't need one capacitor for every chip. Maybe if you've placed your chips closely enough that one capacitor can serve more than one chip, and therefore you can do some optimization that way. In that case, the data sheet gives you part of the story, but not the whole story. Okay, so let's go into voltage regulators. And this part of the lecture is focused on how do we get power to our embedded system, and in this class, what type of regulator do we want to deal with? Okay, there are two basic voltage regulator types that are very common in our embedded design world. And these are the two that I'll mention. We're going to focus on the left column, a linear regulator, but you should be aware of the switching regulator as well. The linear regulator, so it only steps down the voltage. It takes in a higher voltage, and then with some circuitry can reduce that voltage to a lower voltage that the load can consume. The efficiency is low to medium, The waste heat can be high, and the waste heat is a function of how much current you're drawing through the device and how much voltage differential that device has across its input to output. The complexity of the design is low, and that's one of the reasons why it's chosen for this class. In addition, the cost is low, another reason why it's chosen for this class. But if you're trying to design a system which is really efficient at power consumption and is sensitive to the amount of thermal loading that this component adds to the system, the linear regulator might not be the way you want to go. And you might choose a switching regulator, which can give you some additional capabilities. The switching regulator can take an input voltage, step it up to a higher voltage, step it down to a lower voltage, or invert the voltage. It's got some flexibility. But you can pay a little bit for this in that the complexity of the design might be higher. You might find that the cost is higher. But both of these types of regulation systems are very common, prominent in designs, and you can run across both of them in your circuits. There are a few definitions here at the bottom of the screen. SMPS, or switching mode power supply, is one of the things you come across. And then a boost, buck, or buck boost converter are terms that you'll hear specific to the switching to supply. But let's focus our attention on the linear regulator for this class. This is the part that you have in your parts kit, and the one that you'll focus on for a good part of the semester. We don't need to memorize this circuit, but we can at least understand the basics of when we choose a regulator, how it's going to impact what that regulator requires of us as a system designer. In this diagram, we can see that there's an input voltage here on the left of the regulator. There's an output voltage, which is delivered to our load, and then there's a ground pin, which allows current to flow to ground. Inside this regulator circuit, there are a couple of main sub-elements. There are some pass transistors, which allow current to flow from the input to the output. And then there's a feedback circuit, which takes a look at the output voltage that the regulator is delivering and provides a control signal back to our pass transistors, which either allows more current to flow or less current to flow. So if this regulator is supplying a voltage output to a load which is drawing a lot of current, that load is going to be kind of pulling down the voltage at the output. And that will feed back through this control circuit to the pass transistors and allow more current to flow through the regulator to get the voltage back up to the specified voltage. If the load circuit stops drawing as much current, then that feedback loop tells the pass transistors to reduce how much current is flowing through to make sure the voltage doesn't rise up higher because of all the current that's flowing to the load. So this feedback loop is very important because it helps stabilize the voltage at near the correct voltage for the component. If that feedback loop is not quick enough, then I can get cases where the output voltage is fluctuating and not giving me a nice clean voltage to deliver to my load circuits. In this standard NPN, you can see that there are 3 different transistors involved from input to output. And those drops across those transistors mean that in order for you to achieve a particular output voltage, you need to provide a relatively high input voltage that allows that voltage drop to happen inside the regulator. If I take a look at 2 other variations of the linear voltage regulator circuitry, you can see an LDO, or low dropout voltage version, which has a single transistor in the pass circuit, or a quasi-LDO, which has only 2 transistors instead of 3. And as I take a look at these 2 circuits, I can see that one benefit is that I don't have to provide as large of an input voltage in order to get the same output voltage. But I'm also paying a little bit of a price for that. When I compare these circuits, I can see that there are some differences in how they perform. The LDO, which seemed attractive because it doesn't require me to provide a very large voltage input to get the desired output, has a relatively large amount of ground pin current. Specified here as I sub G, that's the ground pin current. The other term for this current is quiescent current. And quiescent current is essentially the current that's used by the regulator and not passed to the load. So if the regulator consumes some current, that quiescent current is power lost because it's not being delivered to the load for actual work. The other characteristic of this LDO is that the amount of current that it can source to the load, I sub L, is relatively modest, 1 amp. However, if you have a design which doesn't require very much current, you can accommodate a little bit of power wasted through the ground pin, then maybe the LDO regulator is a very good choice for you. And the yellow box here at the bottom mentions that it could be pretty interesting to use for a battery-powered circuit because the battery voltage doesn't need to be very much larger than the output voltage from the regulator in order for the system to work. If you had 5-volt integrated circuits in your design, then you need to provide an input voltage to the regulator which is higher than 5 volts. Well, a very common battery voltage is 6 volts. So if I could hook up a circuit which allowed me to operate off of a 6-volt battery, that might be really interesting to me. However, if I tried to implement that with a standard regulator, a standard linear regulator, I'd find that I couldn't do it with a 6-volt battery because I need to provide a larger differential between input and output of that regulator than I do on the LDO. Now, if I compare that LDO characteristic set to the quasi-LDO, I can see that my V sub D, which is the dropout voltage, has increased a little bit because now I have 2 stages of pass transistors to deal with. But I've also reduced the amount of ground pin current, and I've increased the load current that I can source to my load. So some improvements there. When I go all the way to the full standard linear regulator, I've increased my dropout voltage a little bit more. I now have to provide an even higher input voltage. My ground pin current looks pretty good. It looks similar to the quasi-LDO, but now I have further increased my load current. I can, provide a tremendous amount of current to the load. That ability doesn't come for free. Obviously, I've got a large voltage drop between input and output, and the thermal loss there can be significant. So I have power lost in my regulator, which is an efficiency issue, and it's also a thermal issue that I need to consider in my system design. Does anybody have any questions about what dropout voltage is? Basically, remember that I have to provide a differential between input and output. The larger the dropout voltage, the larger the input voltage needs to be to meet a specific output voltage. And quiescent current was the ground pin current, basically the current that's not delivered to the load. This is one other comment about charge usage or power usage in my circuit. This is an idea of taking a regulator, in this case this LP2954 regulator, and instead of hooking its input voltage directly to the battery, I've hooked it to the battery through a FET, a field effect transistor. And that field effect transistor can be controlled with some type of signal. In this case, a signal called on, which could be derived from a hard switch that you flip on and off, or could be derived from the output of a digital circuit somewhere else. The advantage of this type of circuit is that if I do not activate the on signal, then the FET does not allow the regulator to draw charge from the battery. And I can be very power efficient by doing that. Once I've turned on the FET and allow current to flow, then the regulator will provide the nice 5-volt output to be used by the load downstream. If you are designing an embedded system where power, control of the power and battery life is important, this is one of those techniques that you might want to consider is power gating, turning off that downstream power users through switches. Okay, so when you are trying to select the best regulator for your application, here are some of the characteristics that you can consider. What's the maximum load current that you need to supply? What type of voltage source are you using as your power input? Is it battery or AC wall adapter? How much precision do you need to have on your output voltage from the regulator? Quiescent or idling or ground pin current? How much current is lost in the regulator itself? And how much are you willing to lose? And then any special features that might be present on the regulator, such as a shutdown pin or an error flag or protection circuitry that prevents the regulator from being damaged in the event that you've drawn too much power or it gets too hot. There are lots of websites with good information about linear regulator designs on the web, and I think it's definitely a topic of interest. So if you are going to be doing any type of power delivery or hardware design in the future, this is a topic I would recommend that you spend some extra time studying beyond this class. So let's spend a couple minutes discussing a specific linear regulator. This is some extractions from a data sheet for a family of regulators. We'll talk about it as the 7805 regulator, which is part of the LM7800 family, also known as an LM140 or LM340 type chip. You could go out to a device manufacturer and buy many different types of regulators which meet the same spec. We'll focus on the 7805 for today. The 7800 series component comes in various versions that can support different types of output voltages. Our focus is going to be on the 5-volt version, but the other regulators in this family are just tuned to support those other voltage rails. And these come in a TO220 package, which is a mid-range package. It can handle a decent amount of current, but it's not as powerful or capable as a TO3 package, which is larger in size. Our typical application is highlighted in the blue box on the top left, where we provide an input voltage to the regulator. It provides us an output voltage, and then we have a ground, which is used throughout our circuit as a common ground reference. There are two other components shown in this simplified diagram. One is an input capacitor C1 here, and the note down below says the C1 capacitor is required if the regulator is located far from the power supply filter. Basically, this is providing a very close capacitor to the linear regulator input to filter out noise before it goes into the regulator. And by filtering out noise, we're basically improving the performance of the regulator. We're allowing it to do a better job at managing the voltage that it delivers to the rest of the circuit. C2 at the output says, the comment says, although no output capacitor is needed for stability, it does help transient response. So it says, if needed, use a 0.1 microfarad ceramic disc capacitor, which is a decent performance capacitor which can handle high frequency burst and give you quick response from the output of that regulator. It says that no output capacitor is needed for stability. Well, they've handled the stability thing by the internal circuit design, but stability is important to us because if we don't have a stable electrical circuit, you're going to get oscillations in that control loop, which allow the output rail to oscillate and go up and down. And what we're trying to do is eliminate those types of oscillations and have a nice, steady VCC rail as closely as possible. You can use this regulator in other forms as a current regulator or adjustable output regulator, but we're not going to use it in those ways. Let's just focus on this simple application. If I take a look at the data sheet, you will see that the data sheet is a shared data sheet. You can see that there's a column here for a 5-volt version, a 12-volt version, a 15-volt version, and this is because this is a family of regulators. You can have very similar characteristics, similar operational characteristics, but just tuned for particular output voltage levels. One thing I'll point out is that this is one of our first excursions into a data sheet this semester. But understanding data sheets, being comfortable with dealing with data sheets is a good skill to have. And what I've often found is that students coming into this class may not have spent very much time studying data sheets in the past. They've looked at a data sheet to find one particular piece of data and that's it. What I will say is that by practicing our use of data sheets this semester, we are going to gain a little bit of skill at understanding, hey, wait a second, this data sheet is specifying a lot of things. I can ignore a lot of it and I can focus on a few key characteristics which are necessary for me to do a good job at judging how to use this component in my circuit. If I take a look at this page of the data sheet, there's a few characteristics that I'll point out. The first one is VO, output voltage. And you can see that for the output voltage, there are a few different conditions that are mentioned here. The first one says T sub J is 25 degrees C. What is T sub J?
Junction temperature.
Junction temperature. What does that mean? Inside the package, the TO220 package that this part comes in, inside that package is a piece of silicon. And what we're talking about is the junction in that silicon and the temperature that that silicon is operating at. And T sub J at 25 degrees C is a very modest temperature. That's room temperature. That's not really exercising this chip. But what they're saying is if you are basically drawing almost no current from this chip, it's operating at room temperature, then its typical output voltage will be 5 volts, but it's still within spec if it's as low as 4.9 volts or as high as 5.1 volts. Those are all acceptable from the device manufacturer's standpoint. If you consider the use of that chip at different power conditions and different current output levels, you can see that the specifications change a little bit. Now the manufacturer says across that range, there's a little bit wider range of acceptable output voltages that you'll see that is considered normal. If you start your design with a component which is at that 4.9 or 4.8 level, you're basically eating into your noise margin or your margin a little bit in your design, because your processor will be spec'd to operate at a certain level. And if we reduce the output voltage, we're maybe eating into the amount of voltage that we are allowed, noise that we are allowed to have on our voltage rail. But because of margins, it's still going to be fine. Even if we get a component anywhere in this range, we'll still be able to use it just fine. Line regulation is our next characteristic. So line regulation is referring to the amount of change you see on the output of a regulator as a function of what's happening on the input of the regulator. So if your input voltage supply to the regulator has some deviations on it, how much of that change at the input makes its way through the regulator and is seen at the output. It's a characteristic of how well the regulator is regulating the voltage. And this is saying that for an output current of 500 milliamps and a delta V in ranging across this range from 7.5 to less than 20 volts, that they're specifying 10 millivolts of noise seen on the output rail due to line regulation. The next element is delta V out. This is load regulation, and this is basically how well does the regulator control its output voltage when the output current fluctuates. So the load circuits that are connected to the regulator have changes in how much they're drawing, and how well does the regulator hold its VCC at a constant output as a result, or during that time. And this is again showing you some characteristics where there's a certain amount of noise that is acceptable and expected on the output voltage as a function of load regulation. And then at the bottom of the screen, there's a thing called quiescent current. And again, this was the ground pin current or current that's lost in the regulator, used by the regulator, that's not passed to the load. And this says over the temperature range of the device, you can see that it's potentially consuming 6.5 milliamps of current through the ground pin that it's not passing on to the load. So there's a certain amount of power dissipation that you need to deal with. Looks like I've just continued. The next page is a few more characteristics, and let me just focus on dropout voltage for a moment. You can see that the spec here for dropout voltage says that for a junction temperature at 25 degrees C and 1 amp of output current, that it requires at least 2 volts of differential voltage between input and output in order for this regulator to work according to spec. But that's not where we just focus our attention. We're going to focus our attention on providing an input voltage which can handle all the different characteristics which can influence the output. And what this is saying, in order to maintain line regulation, we should see at least 7.5 volts at our input. So what you should see this semester is as you're feeding voltage from your wall adapter to the regulator on your board, you're trying to get at least 7.5 volts to the input pin of your regulator. There'll be a little bit of voltage drop due to the diode bridge that's present at your input. And then depending on how much load current you're drawing from that wall adapter, you're going to see quite a range of voltages from that wall adapter. An open circuit where you just have the wall adapter connected to, thin air, you might see an output voltage from that regulator that's 12, 13, 14 volts. But once you start drawing current from that wall adapter, you'll see the voltage come down from that wall adapter maybe into the 10 or 9 volt range. And as long as you maintain at least 7.5 volts at the input of your regulator should work well. Here's a few definitions that I've already talked about. Please refer to those and make sure that you're comfortable with those terms. Protection diode. The datasheet talks about a protection diode. We have this element in our circuit diagram. The question is what is its purpose and why would we have this in our design? The datasheet says a fast diode D here at the top is recommended for an output capacitance C out of greater than 10 microfarads. What is the purpose of having that diode?
It is providing a feedback from output to input, but not from input to output.
Yeah, it's directional from output to input, but if I think about it, wait a second, I thought I'm providing at least 7.5 volts at VN, and I'm getting 5 volts at Vout. Why does this diode ever come into play?
If the load value changes such that there is excess current at the output generated, that would just go back at the input to save.
So if somehow I get out of regulation and my Vout increase, is that what you're saying? So that's not a scenario that I'm going to focus on. I think what we'll assume in this discussion is that during operation of the linear regulator, I'm not going to have great fluctuations in Vout that would cause Vout to climb above 7.5 volts. Is there any other reason why you could picture adding in a protection diode like this? Yes, front row. I can't hear you.
I just said, but it seems like with the capacitor, there could be cases where it accumulates enough charge to drive V out above 7.5, which could break the regulator, but not sure exactly what scenarios that would happen in.
Yeah, the capacitor doesn't just keep building up voltage. The regulator is going to force it at a particular voltage level, and it's going to stay there. But what happens when you turn off power? And that goes away. That goes down to 0 volts. Now you've got a scenario where, depending on how much capacitance is sitting out here in your circuit, it could be holding the voltage up. And until there's enough drain to pull that charge off those capacitors and drain that voltage down to 0, you could have a scenario where the output voltage is higher than the input voltage to that regulator. And what you're trying to do is prevent large amounts of current flowing back through that regulator and damaging it. So what this is saying is, if you do have a scenario where, whether C out that's tied directly to the regulator, or a distributed V out, which is all those decoupling capacitors that I've hooked up to my load circuits, hold enough charge that I might need to provide some alternate path for that current to go to ground and discharge quickly when I turn off power. So depending on what you've chosen for a regulator, they may have protection built into the regulator, or they may recommend the addition of a diode like this to help protect the circuit. But that's one of those things that you start asking yourself as a designer is, okay, I've got the base functionality figured out, but are there side effects, or are there other conditions which could damage my circuitry that I need to be considering? And then you add in elements to help protect for those situations, and that's what you see here. The TO220 package shown on the right is what we're using in our parts kit. Remember that you need to pay attention in your data sheets as to what view you're looking at. Sometimes you'll see a bottom view, sometimes you'll see a top view, but make sure that you get your pins correct from the perspective of the data sheet. Now, before we take our break, I'll talk briefly about heat sinks. Heat sinks can take many forms, and the purpose of a heat sink is to try to keep the device temperature down below its maximum value. And one thing I'll highlight here is that silicon life is highly dependent on temperature. So if I operate my silicon at a high temperature close to its rating, then over time that silicon will degrade and may change its characteristics some. Silicon does this, it has aging effects, and it changes over its life. But if I can do a better job at keeping the silicon operating at lower temperatures, then I kind of extend its life and I don't stress it as hard. What this couple pages talks about is the fact that when you're dealing with heat sinks, you're trying to figure out a way to move heat. You're trying to move heat from the package of the silicon that you're trying to cool to somewhere away from that package. And it's often into the air or farther away from your device. In order to calculate the type of heat sink that you need, you'll need to know a few things, like what's the maximum junction temperature of the silicon that you're dealing with, or where you're comfortable allowing that junction temperature to rise to, the amount of heat or in watts that you're trying to dissipate, the characteristics of the ambient surrounding. So what is it like around your device? Is the air hot? Is it cold? Is there moving air? Those types of characteristics impact your choice of a thermal solution. And then what they talk about is thermal resistance. So this term, theta JA, is the thermal resistance from the junction of my silicon to ambient. And to get from the junction to the ambient, it has to go from the silicon into the package, from the package into the heatsink, and from the heatsink into the ambient. And so there are these thermal interfaces that happen as heat moves from that silicon junction out to somewhere where it's dissipated. And those thermal resistances are important to us. The total thermal resistance in our design is the sum of those three thermal resistances of our interfaces. So the first one, theta JC, is junction to case of the package on the device. The second one, theta CS, is from the case to the sink. And the third one, theta SA, is from the sink to ambient or air. The job of us as in terms of providing a thermal solution is to provide a theta JA low enough so that I can move the heat out and keep the temperature of my silicon low. What you see here are some typical values for thermal resistivity of different types of materials. And you can see copper is quite good. It's got a very low thermal resistivity. So you see copper used to try to move heat across a system or away from a heat source. And as you go down this list, you can see that thermal resistivity increases quite a bit. And what do you see here for just air? A large amount of thermal resistance. So just because you've got a device exposed to air does not mean that thermal energy is going across that boundary very efficiently. So what we're trying to do is to control our thermal resistivities of each of those interfaces to the extent that we can. If we consider theta from junction to case, this is inside the part that we've chosen. Do we have any control over that? No. The only thing that we can do is to choose a different part that has a lower theta JC. We can't change the theta JC externally as a system designer. What about from case to sink? So we can potentially influence this, and this is one of the things to consider. The heatsink that you have in your parts kit can be used by you. You may find it to be important, you may not find it to be important, because you can actually use that TO220 package from the regulator to source quite a bit of current, and probably through the first 2 or 3, 4 lab assignments, you'll have enough capacity to use your regulator without a heatsink. But I've included a heatsink in case you want to use it. If you look at the heatsink, you can see that it's physically attached to your package. And in this case, it looks like it's just attached through pressure. So because of how the spring clips are designed on the heatsink, it's providing some pressure to the surface of the regulator and allowing us to get heat out of the package. But what I'll point out to you is that just because it looks like I've got a heatsink on there does not mean it's working efficiently. And what you should be aware of is at that interface between the regulator, and the heatsink, there are actually all these different little teeny microvoids. So a little bit of spaces in between those two surfaces. And those microvoids are full of dead air. And the thermal resistance of that is very high. So just because you can't see those microvoids does not mean that they're not there and that they're not obstructing the flow of heat. So one of the things that you might do is to use a thermal grease. You can see that silicone grease is shown here, or you might use some other type of product called a TIM. It's a thermal interface material. And it's basically there to provide a low impedance path for heat to flow from one side to the other. And so you might see mica or mylar or some type of rubber interface between the heatsink and your package. And the reason for having that there is because it provides a lower thermal path, lower impedance path for thermal energy to get through that. I don't include the mica, mylar, silicone grease in the parts kit, but I often provide silicone grease available in the lab. If you want to use some, you can ask the TA to see if we have any. But at least just even applying the heatsink to the regulator will at least provide some benefit. And if you need more benefit, then using a TIM, thermal interface material, could take you even further. The other thing that this shows is that movement of air in your system can drastically improve the thermal performance of your system. So even if you have just a little bit of airflow through your system, it's moving heat away and it's creating a differential in temperature that allows heat to flow from the silicon out to the other, to the world. So if you as a system designer can allow a little bit of airflow in your system, you will see it perform much better than if it's an enclosed environment which just traps the heat and doesn't get it out of the system at all. A smartphone can be a very challenging environment, because if you think about the electronics in a smartphone, they are typically in some type of sealed package which does not allow airflow. And so you have to deal with the fact that temperatures are rising in that cavity and that you're stressing those components harder than you might have to if you were in an open design. Does anybody have any questions about the concept of heat sinks or how we might want to consider their use in a system? Front row.
How does mica reduce the air gaps? Is it like in a powdered form or some like gel, or is it just like solid sheets?
You know, I'm not sure about the physical construction of that material, but in general, those joints are compressible. So if you look at the mica or the rubber and you put them between a heat sink and a package, you typically use some type of machine screw or something to tighten it, and you're forcing those things in tight contact with each other. And that's my assumption there as well. Okay, so with that, we reached a quick break. To joiners, you can take a quick break and then we'll start up again. So let's take 10 minutes and then we'll start. What the exact accuracy is, the cost of your system design is most important. And so if you can design in elements in your software design which can accommodate variations or fluctuations in your clock source, then you can get away with a cheaper design, which is ultimately allowing you to be more competitive in the market. So the crystal has very low cost, and the crystal oscillator module mentions that it's insensitive to EMI and humidity. No additional components need to be added when you deal with a crystal oscillator module. Some of the disadvantages of those first two are that the crystal, because it's not a closed package which has a can around the electronics, mean that it's more sensitive to EMI. It has vibration and humidity sensitivity. And then if you want to match that crystal to the oscillator module, which is actually inside our processor chip, then there's impedance matching that has to take place. If we deal with a crystal oscillator module, one of the downsides is its cost. It can be pretty expensive to put a crystal oscillator module in our design. It's very easy. It's rapid for prototyping. You just take this oscillator module off the shelf, plug it in, provide it power and ground, and it gives you a nice clean TTL clock signal that you can use to drive your components. The downside of it is, besides cost, that the signal strength of that TTL clock output is very strong, and it introduces a lot of noise in and outside of your system. So it can not only you can see effects across your electronics in terms of the noise introduced by that oscillator module, but it can radiate, and nearby or even a little bit further away electronics could be picking up the noise that's generated by that clock source. There are a few extra slides in this that I'm not going to spend some time on, but it's there for your reference later. But for instance, this talks about some of the different oscillator characteristics and vibration modes. When you're dealing with crystals and oscillators, there are lots of different ways that you might find the physical construction set up. But at the end, your ultimate goal is to end up with an oscillating signal at a particular frequency, which is hopefully tightly controlled. The way that they achieve that can vary, and what these diagrams on this page and next page show are that there are various cuts in the material that allow you the physical oscillations to give you the electrical frequencies out. If we take a look at how crystals are constructed, the top left diagram is what you usually see when you're buying a component from an electronics distributor. But if you take that can off of the device and look at what's happening inside, what you'll see is that there is a crystal that has been sliced in a particular way and connected between your electrodes. And this is a complex mechanical element which, when given an energy source, oscillates and gives you a fundamental frequency or overtones. What the diagram at the bottom left is showing is the original quartz crystal that was grown, and then it was cut and sliced in different ways to give you the thin pieces that they put inside the crystal package. And there's another way to look at it. When you buy a crystal from a distributor, you will sometimes see that it has a particular name associated with it. For instance, here's a CT cut, here's an AT cut, a BT cut, and it's referring to the exact angles and positioning of the cut of the quartz crystal that was used to manufacture that crystal. Again, this just shows you a little bit more about how the part is manufactured. The point here is that there is a physical element inside that package which is sensitive to vibration and shock, and you could damage that thing if you dropped it or allowed it to experience sudden acceleration. This table is again just to point out that there are wide numbers of oscillator components available, and you will have to go through and choose characteristics of your component that matter to your design. The right-hand column here says major application, and you can see that for this choice of components on this page that they have targeted applications. Some of them are surface mount components, which are intended for very small mobile devices. Some of them are through-hole components, which are designed for lower cost, larger components, which aren't so sensitive to the ultimate size. If we can compare that crystal package to a crystal oscillator package, you can see a little bit of a difference. The crystal oscillator package is larger in size. It has a can or covering over it, which is grounded to try to hold in the electromagnetic energy. And then you can see basically the crystal is located inside the package along with some simple circuitry, which squares up the waveform and adds drive strength to output a very strongly driven signal. A couple of terms that are associated with crystals, oscillators, and clock circuits in general are included on this page. One is EMI, electromagnetic interference. An associated term is EMC, or electromagnetic compatibility or compliance. And these are concepts of trying to make sure that when you are putting together an electrical system that you are not susceptible for interference from other emitters, and that your system is not a strong emitter that could be damaging or interfering the operation of electronic circuits nearby. The other term that I'll point out is SSC, or spread spectrum clocking. This is a concept which is used in many applications. And what this is saying is that instead of outputting a frequency at one fixed frequency point, they vary the frequency a little bit so that it actually spans a range on the frequency chart. And by spreading the range of frequencies out over time, you're spreading the energy emitted from that circuit out so that your overall energy at any one particular frequency is lower, and that you can make this component more compatible with other electrical designs. Enabling spread spectrum clocking is one of those things that you find in circuits to try to improve its ability to meet FCC specifications and allow you to ship a product that's not a large radiator and interfering with other nearby electronics. If we consider the oscillator circuit for our 8051 board or processor, we start by understanding that there are a couple of pins on the processor which are relevant and important to us. The X-TIL1 and X-TIL2 pins are connected to internal circuitry inside the 8051 chip, which provides the oscillator portion of the components. And then external, we have this large quartz crystal, or potentially a ceramic resonator, and then a couple of load capacitors, C1 and C2. The first thing I'll point out is that when you're writing or drawing your schematic for this class, we expect you to put down component values everywhere, not just a reference designator like C1, C2, Q1. We want you to also put down the component value. The reason for getting into the practice of this is that as somebody is looking at your schematic, if they understand what the component values are, they can do some basic calculations. If they know your fundamental frequency of your crystal, then they can calculate, oh, I know that the clock is going this fast and my instructions take so long to execute. If you don't include that detail, then they'll have to go and ask you the question, and we don't want that in this class. So please make sure that you properly notate your schematics with that type of detail. The next thing to comment on is that C1 and C2 are nominally 27 puff, 27 picofarads. So your parts kit you'll find will have 3 of those capacitors. The first 2 you'll put as C1 and C2, but you might find that you need to do some tuning. And so we provided you a third one for the use of tuning, and we'll look at that shortly. These components should be placed close to the oscillator circuit inside the processor. So what we want is the external crystal and load capacitors to be located pretty close to the Xtal1 and Xtal2 pins on our device. If we put it a long ways away, now we start introducing larger inductance because of the loop areas involved, and that complicates our tuning of the network. Oscillator startup is an important concept, and I want you to be aware of what we're talking about here. When you first turn on power to your system, the VCC rail starts at 0 and goes up to 5 volts, and that's what I'm trying to represent with this line, a sharp transition from 0 to 5. But you can see that between the vertical blue bars here on this page, the oscillator is just starting to oscillate. And you can see that it starts to transition larger and larger, and finally it starts to build up till it's larger and full-scale oscillations. In these 4 examples, you can see it can take a variable amount of time for those oscillations to start and build up to a good size value. The oscillator isn't useful to us until those oscillations have built up to a large range of voltage differential between max and min. In the period of time between the 2 bars on each of these screens, the oscillator is really not of great value to us in our circuit. And if we allow our circuit to start trying to execute, our state machine and the processor start trying to execute during the time between those 2 blue bars, we are asking for trouble. The circuit may not perform correctly, and we may lose control of it right from the beginning. And that's absolutely against the goal that we're trying to achieve in being a good system designer. Our goal is to hold the processor in reset until the oscillator has come up and is stable, and then only at that time allow the processor to come out of reset and start executing its code through the state machine functionality. You can see that there's quite a bit of variability in these 4 examples. A quick comment about one of the forms of timing element, ceramic resonator. These are typically pretty inexpensive. They are functioning as a mechanical resonator. Some resonator packages have 2 pins like shown here. Some have 3 pins as shown here. The ones that have 3 pins include load capacitors inside of them. So as one component, they provide all that capability external to your 8051 or other processor. If it only had 2 pins, you'd still need to connect on load capacitors to build your entire oscillator network. I'm going to skip this. You can look at it in the notes, but basically talking about the resonator characteristics as compared to a quartz crystal resonator. And then let's remind ourselves of the reset circuit on our 8051. The reset pin on the processor is an active high signal. So if we want to hold the processor in reset, we give it an active high voltage, and we give it a high voltage, and that holds the processor in reset. As the voltage on the reset pin drops below the threshold of the reset pin, the processor comes out of reset and starts trying to execute code. So this diagram is showing two different types of reset. We have a power on reset, and the components in this circle or oval, the capacitor and the resistor, perform the power on reset capability. And this reset key out here provides a momentary reset or a runtime reset, so that after the system is already powered up, you have some way to reset it without turning off power to the whole system. This reset functionality is critical. If we don't have good resets in our system, we cannot expect the system to work correctly. When you're reading the datasheet or reading the articles talking about oscillators in our embedded systems, you should have read that the minimum reset time has a spec. What is the spec for the minimum reset time of the 8051? What's that?
More than 2 machine cycles.
Yes, so this part down here says 2 machine cycles plus what?
Time required for supply and crystal to stabilize.
Yes, plus the startup time of our oscillator circuits. So we want to make sure our oscillator circuit is up and stable. Once it's at that point, we want to make sure at least 2 machine cycles have passed, and then we let the processor out of reset. Now, in actuality, which piece of this dominates your time? Your startup time might dominate your machine cycle time. The machine cycle time is actually very short. The oscillator time can be quite a bit of time. And so we can't ignore it. We have to absolutely make sure that we've got enough time allocated in our reset circuit to allow the oscillator circuits to become stable. How do we determine that? Well, you don't determine it up front. You're not sure exactly how long it's going to take. You have to do some measurements. In our lab experiment, I'm asking you to do a few experiments to take a look at what the characteristics of your system are when they come out of reset. But in a design, what you might do is you're going to build a whole bunch of systems and you start characterizing them. You start taking a look. How long does it take this system to come out of reset? And is there any tuning I need to do to my oscillator circuit? And once I've determined what the startup time of my oscillator looks like, then I can choose my reset values to ensure the processor stays in reset long enough upon power on. Those are tuning of our system that we do before we go to production of our product. Once we've tuned the system, we know exactly how it should be performing and what the correct values are. Now we can build our volume production boards, all with that optimized value, and then our customers should have a good experience with the system at that point. One thing to be aware of is the threshold of our reset pin. So if you take a look at what's shown inside this blue box, it says input high voltage for X to 1 and reset is 0.7 VCC for the Phillips part. This says that the manufacturer says that if you provide at least 0.7 VCC to the reset pin, it will go into reset. It does not guarantee it comes out of reset at 0.7 VCC. It might come out of reset at 0.65 VCC or 0.6 VCC. I don't see that spec here. But at least you understand one piece of the characteristic of that reset pin. And because you know this, you can do some calculations to calculate how long does it take us to get down to 0.7 VCC, and therefore how long am I guaranteeing the processor staying in reset when I force it to that state at power up. The other thing to point out on this data sheet is the RRST value, the internal reset pull-down resistor. The 8051 architecture actually has a resistor built inside of it to ground, and that's this RRST. That resistor is a diffused resistor that's in the silicon, and it is there to try to simplify our external circuit elements. If I don't have very particular requirements on the reset timing, and I just want low part count and low system cost, I might try to eliminate external circuitry, like getting rid of the external resistor and external reset line, and only connecting a capacitor to the reset pin. Because there's an internal resistor, that provides me all the capability I need for a power on reset, and I don't need to add extra cost to my system. However, if I want to more carefully control the reset characteristics of my board, I now need to consider adding an external resistor. The data sheet that we looked at here said that the resistance for our RST has quite a range. Take a look at that. 40 kiloohms to 225 kiloohms. That's a huge tolerance on that component. That means that I could take two different 8051 processors spec from Philips, put them in two different systems, and they could have RC time constants which are drastically different from each other because of the diffused resistor that's inside of them. If I was interested in designing a system which was more tightly controlled and had more predictable timing on its reset release, what could I do? Front row?
Could measure the reset resistance.
For a particular part, I could measure the reset resistance. But if I was trying to design something that was going into production, I wouldn't be able to measure the reset resistance for all those boards. What else could I do? Is there anything I could do to reduce the dependency of my RC time constant on this diffused resistor that's inside the silicon?
We can make the R value of the RC very high so that the resistor in the silicon value is significantly low compared to this, maybe. And
the right concept, but significantly high compared to this. What we want to do is have a circuit which is dominated by some other element rather than the resistive component inside the silicon. So what do you see in this diagram? If I add on an external resistor, which is smaller in size, our RST could range from 40 k ohms to 225 k ohms. And my external resistor at 8.2 k ohms is much smaller, which means it's much stronger, which means it dominates the parallel combination of those two resistances. If I have 8 k ohms in parallel with 40 k ohms, what's the equivalent resistance of that roughly? It's close to 8 k ohms. It's not so dependent on what the actual value was on the RST value. So if I had to have a situation which was more tightly controlled, I could achieve that in a pretty low-cost way just by adding on an external resistor which dominates that resistance parallel combination. Does that make sense? If it makes sense, raise your hand. Great, thank you. Now let me talk about something else that you might run across when you're doing our lab work. We are starting to learn about some of the special function registers in our processor, and one of those is the PCON, or power control register. The power control register has a couple of special bits. One is called PDE, or power down enable. The other is called idle. And by writing a 1 to one of these bits, you can force the processor into a lower power state, conserving power. The table at the bottom is from the user manual, but it shows you the state of ALE and PSEN lines depending on which of these lower power states the processor went into. There's another table, I think, that shows it in a little different light, but basically the point here is that it's possible through a bit write to a special function register to put the processor into a low power state. The question to you is there any way for that processor to mistakenly get into a low power state? And the answer is yes. Here's a scenario. Let me see if I've got a diagram. Here's a scenario. And this is something that you'll start implementing in Lab 1. In Lab 1, you get your hardware kit. you hook up your processor, you hook up your reset clock and power source, your linear regulator, but you haven't hooked up all the other circuit elements yet. And what this diagram is showing is that the code storage device called EEPROM here in this diagram, but could be an NVS RAM, could be any other type of code storage device, is not currently present. I've got the dashed lines around it. The processor then has basically some lines that are connected to the board, but not connected to any other integrated circuits on the board. The condition that you might experience is that you turn on power to your system and the pins on the processor start to come up and start to seemingly operate. What should you expect to see on ALE at this point in time? If I turn on power to the system, it's got its clock source, it's got its resets, it's got its linear voltage regulator. What should I expect to see at the ALE signal?
Be high.
Why would it be high? It's actually going to be toggling. And one reason for it to be toggling is that unless a particular instruction is being executed, ALE is showing you a frequency that's 1/6 of the processor frequency. This is shown in the data sheet. So if I have an 11.0592 megahertz clock crystal, how do I determine whether the clock crystal is up and running correctly? Do I connect a scope probe to my XTIL1 or XTIL2 lines? Let's take a look at that circuit again. Here's my oscillator circuit. If I turn on power to my system and I want to test to see whether or not my oscillator is running, can I just take my oscilloscope probe and connect to XTIL1 or XTIL2? How many people think yes? Raise your hand. Okay. How many people think no? Raise your hand. Okay. So why do you think no? If somebody's speaking, I can't hear in the classroom. I don't know if it's muted by the operator or not.
I'm saying I think none of the two terminals are like included at reference. If you're measuring the waveform, we need like one of them and a ground.
So if I want to measure a voltage at one of those pins relative to ground, I could do that. But I've got a problem if I try to do that. The oscilloscope probes that we have in our lab are passive probes. What's a characteristic of a passive probe?
Doesn't
They have a capacitance in them.
Absolutely, probe capacitance. Does anybody have a feel for what the probe capacitance of a passive probe might be?
in picofarads?
Yep, maybe 10 to 50 picofarads would be a common range. What's the value here that I've got for my load capacitors? About 27 picofarads. If I take a probe, an oscilloscope probe, and I connect it in to try to measure XTIL1 or XTIL2, I'm adding in a capacitor that's roughly the same size as the load capacitor that's already there. Do you think that could influence my oscillator circuit, my tuning? Absolutely. I could be messing up the tuning of that feedback circuit, that network that's allowing me to have a stable clock source. So one thing you might experience is that you come in here and try to measure it, and it stops working. You don't see anything. So question to you is there another way to get the measurement to determine whether or not my clock source is functioning correctly?
ALE.
ALE. So we talked about it on the other slide. Why do I measure at ALE?
Has a lower frequency. It doesn't.
It does have a lower frequency.
Not that sensitive to like capacitance value, like which is put by the probe, like added by the probe.
Okay, but that's not because it's a lower frequency signal. It's because it's an actively driven output signal. It's intended to be loaded by some other circuits. So instead of trying to use a probe on one of these sensitive X1 or X2 lines, I could get the information I want by looking at ALE, which is an actively driven output and is strong enough to be loaded with a 27 picofarad or 50 picofarad scope probe without changing its characteristics. So I take my scope probe, I hook it up to ALE. What should I expect to see on ALE if my oscillator circuit is working correctly?
Of the frequency.
1/6 of the crystal frequency. So I should be able to see something that is 1/6 the frequency, which is, midway between 1 and 2 megahertz in size, and it should be pretty stable unless the processor happens to execute an instruction which was a deviant. Most instructions allow ALE to operate at 1/6 the frequency of the clock source. So for you, when you're measuring the crystal oscillator in your lab, measure ALE, and that's where you're going to get your measurement point. Now the question is, what happens when you measure ALE and then it stops? It's not. You may grab onto it and it's at the correct frequency, and then it stops oscillating. What could be happening? What was the answer? I heard somebody answer, but I couldn't hear what it was. Okay, let's take a look at this diagram again. I'm measuring ALE, but it stops. We learned about these 2 bits, and the question is there any way those 2 bits could get set? One of those 2 bits gets set when I don't have anything tied to the bus? And the answer is yes, it could. It's possible for one of those 2 bits in the Pecan register to get set. How could that possibly happen? I don't even have a code storage device hooked up to my bus yet. Any ideas?
Noise.
Noise? How could noise cause this?
I just read somewhere that it can cause changes in some noise values, or spikes can cause changes in the memory address and program counter.
It's true that noise can adjust things like the values that are stored in memory. Just a question, I mean, does it seem like a stretch of the imagination to think that it could change those 2 particular bits in Pecan? I mean, there's all sorts of bits in that processor. Why would it change one of those 2?
Floating pins can be anything unless P0 has its pins pulled low or pulled high with internal resistors.
It could be anything, but again, doesn't it seem far-fetched that it would happen to be something that writes to one of those 2 bits out of all the bits it could possibly write to? This is actually a real problem that people have experienced in this class. And one of the things to think about is that when the processor comes out of reset, what's the first thing it does?
Origin.
It
Reset.
reads from what address?
Origin. 0.
Address 0, the reset vector. So it tries to read from memory at address 0. In order to read from memory at address 0, it has to put out the address 0. So it forces P0 and P2 to a 0, waits, and then tries to read back in the opcode from address 0. Well, what does it read back in? There's no chip out here that's actually driving data back to it. So it reads its P0 value, and P0 is probably floating at something close to a 0 because that's what was just previously driven out of P0. So it reads back in a 0. Well, what is the next thing that happens in the state machine of the processor? After it reads from address 0, it increments the program counter, and what's the next fetch it does? Address 1. So it emits a 1, and then it reads back in the value. And what do you think it reads back in when it had just previously written the address 1 out?
1.
A 1. So now you can see that there's a situation where just because the processor is using its state machine, it's outputting something and then reading it back in. It could be going through a variable set of reads from data, from the floating point P0 lines. It doesn't always have to be reading the same values from P0. It could be reading a changing set of values. And over time, it could read in a change of values that happens to decode to a move instruction to the bits of the pecan register. Now you say, oh, it could take a long time to do that. Well, let's think about processor speeds. How many instructions are being executed in this processor? If the clock speed is 11 megahertz, a machine cycle is about 1 megahertz. So a machine cycle is about 1 million machine cycles per second. So it can go through all these combinations really quickly, and before you know it, it finds one of the combinations which hits the pecan idle or PDE bits and shuts it down. We want to avoid this because if we're tuning our oscillator circuitry, we need to have the system up and running in a stable way. So what can we do? I heard somebody mention if the P0 lines were low or high, then you wouldn't hear this noise or read this noise back in. What could we do to P0? We could tie a bunch of pull-up resistors to it, or maybe less than a bunch, just 1 or 2 strategically placed pull-up resistors, and make sure that whatever the processor reads back in does not decode to some instruction which writes to the pecan register. And what we've done in the board that we've given you is allowed you a pull-up resistors set, a SIP package, which pulls up P0, and every time the processor increments the program counter, it's going to read back an FF. And the FF decodes to a benign value, which does not cause a power down enable or an idle bit to get set. And that allows you to measure ALE every single time and get a good reading on whether your oscillator is working correctly. When you first solder in the 27 picofarad values to C1 and C2, some of you may have complete operational oscillator at that point. It may work perfectly fine. Some of you may find that it's oscillating at a higher frequency. So instead of 1.8 megahertz, it may be oscillating at 3.6 megahertz. If it's oscillating at something other than 1/6 of the crystal frequency, then you need to fix it. You need to tune it. You need to adjust the load capacitance, get it to a point where every single time you turn on power to your system, it always comes up at the right frequency. That is something you have to do. You have to tune it now because that problem could keep coming back to you as you go through the semester. So each time you change your processor or you change your clock source, you need to tune that so that it always comes up power on at the right frequency. Once you've tuned it for power on reset, you also need to test it for momentary reset or runtime reset. So you keep putting in a reset, letting it come out of reset, and verifying ALE always comes up at the right frequency. If it ever comes up at the wrong frequency, you need to keep tuning it until it comes up right. That is part of your hardware requirement for Lab 1. And then when you get to Lab 3 and you replace your processor with the new Atmel processor, you may have to do one more round of tuning then, because you'll now have a new combination of crystal and oscillator circuit inside that new processor. Okay, are there any questions about this concept? It's important that you understand the general system issues here and how we can address them, and how we can know that by taking a scope with passive probes, we can actually understand what's happening in the circuit, even if we're not allowed to probe right at the crystal pins themselves. Any questions?
With high,
yes, front row.
With high volume manufacturing, do all systems get tuned as they're being fabricated?
It will depend on what the application is, what the kinds of components are that are being used. But our goal in system design is to tune it during the design phase so that you can go to manufacturing and not have to go through that type of precise measurement anymore. You're not going to tune it in manufacturing. You need to tune it in the design phase so that in high volume, you're just checking, did it come up right or not? And if it didn't come up right, you fix the flaw that's on the board. You don't change the component value. You just substitute a part or fix an open trace or whatever is wrong with the board. You're not changing or tuning that value again.
So when you say retune with new processor, you mean new processor type, not another 8051. Like if you tune it for an 8051, it should work for all 8051s?
What I'm saying is that in our lab environment, you are not designing or tuning in the way that you would in a high volume setting. You have one C501 processor that you're trying to tune correctly with hand soldered, less than optimal circuit conditions. And then you're getting a new Atmel processor, which you're tuning, hand tuning to make sure it works. If you were designing that board for a high volume manufacturing, you would test that same implementation on multiple boards to make sure that it did work across a range of silicon. I'm not giving you the capability to do that because you only are designing one board yourself. So there's some differences in what you experience in our lab environment to what you would do in getting ready to ship a product in high volume. Other questions? Okay, let's spend a couple minutes talking about supervisory circuits. We do not have that in the kit, but you'll find this in some embedded systems. The supervisory circuits have three major functions. One is a POR, or a power on reset function. And what this device is doing is it's basically providing us a way to force the system into reset and to allow us to operate from a known good condition at all times. What this diagram is showing us is that as we turn on power to the system and it starts to ramp up, it goes through a period of time where there's maybe a little glitch, and we don't want to allow the processor to come out of reset until that glitch has passed. The supervisory circuit forces the processor into reset for, in this case, 500 milliseconds before it lets it out of reset. This example is showing us a case where there's an active low reset. We know with the 8051 we have an active high reset, so you'd have to adjust this diagram to make it work with the 8051 concept, but the same principle applies. You're trying to hold the processor in reset until the power supply is known good after you turn on power. The second condition is a brownout condition, and that's after you've already turned on power, the system's been operating for a while, but something comes along to cause a glitch in the power supply, and it causes the voltage to drop below the allowed voltage for your silicon. If it ever gets below that allowed voltage, you want to force the processor into reset to make sure that it always stays within spec. And so in this case, the supervisory circuit notices that the voltage came down low, forces a reset, waits a period of time, and then lets the processor come back out of reset in a known good state. The third condition is the microcontroller loses control with a slowly decaying power supply. So in this example, I turn off power to the system, and because there's capacitance out there, the charge starts to drain off the capacitors, and it starts to follow this exponential curve down. And what this is showing us is that the microcontroller loses control when the voltage on the VCC line drops below the minimum acceptable voltage for the processor. However, there may be other components in the system which are spec'd to operate at even lower voltages. An example of that is the serial double EEPROM, the electrically erasable programmable read-only memory that we're going to use in Lab 4. That component can work down at a much lower level, maybe 2.5 volts or 1.8 volts. And because that component is still functional, it will still accept commands or do activities that it sees on its input lines, even if the device that's sending it, like this microprocessor, is out of control and is just sending sequences that it doesn't really want to send. Where this could come into play is you've written a function, a little device driver for your double EEPROM, and if you ever go through that sequence of instructions, it will cause a write to happen to your double EEPROM. Well, it's possible that the processor has now lost control and has allowed execution to get into a function which is writing to the double EEPROM device. If that code executes, the double EEPROM will accept that write as if it was a valid write, and it will update its memory condition. However, you didn't want that to happen because the processor was out of its spec. In this case, the supervisory circuit will force the processor into reset and prevent it from sending out this errant sequence of instructions and corrupting the contents of non-volatile storage that's in the system. Those are three ways that a supervisory circuit could help your embedded system, and they are very helpful. They add cost to your system, so you'd have to weigh whether the value is there for your application. So let's spend just a couple of minutes going through the classroom. I want to meet you. I don't know all your names yet. What I'd like to do is just go around to each of you and have you tell me just a few things. One is your first name. One is any personal interest that you're willing to share, whether you feel stronger in hardware or software, and if there are any specific goals you have for the course. Very simple way for me to break the ice and get to know you a little bit. I will start just to show you what I'm looking for, and then I'd like to just go around and have you complete this so I get to know you a little bit. So, hi, my name's Linden. Personal interests, I have a lot. I love raising my kids and family life. I love to travel. I love music. I'm a musician. I play lots of instruments. I just have a real passion for music. I love the outdoors. I love farming. I love to meet people. I just have a passion for a lot of things, especially embedded systems and teaching. I feel like I'm strong in hardware and software. I've developed a career where I've had a chance to work in both of those things through my working days, and I feel like I can do well in either area. And then my specific goals for the course are to have a good experience with you and to help you through this material so that you become stronger and more capable. I hope to have good interactions with all of you, and hopefully we all have some fun together. So that's what I'm looking for. So if I could start maybe over here on the corner, the gentleman by the wall, if you could just go through and then we'll just go around the classroom.
Sure. So I'm Miles. I moved to Boulder partly because I love riding my bike, and this is the most bike-friendly city that I've seen so far in the States. Other personal interests, since the beginning of, or I guess near end of high school, I always liked having some side project going on with embedded systems. But I noticed since I started working, and I thought that without all the homework consuming my afternoons, I'd spend even more time doing this, but haven't really found the motivation. And so I think tying that into one of the goals for this course is I really want to get inspired again and try and tackle some of these projects on the backlog. I like how we have a final project in store that's open-ended. And then as far as strengths, so I have a software day job, so I guess my software skills are a little better, but I really wish I could do some more hardware stuff, so that's another one of the reasons for taking this course, good hardware emphasis.
Great, thank you. Next student.
Hi, I'm Sain, everyone. My personal interests would be soccer and music. I'm a big soccer fan, and I support my Manchester United. I follow it very closely, and I like writing as well. I write some poetry and stuff, and I feel I'm stronger in software rather than hardware, and which is why I'm part of this course. And yeah, like pretty much, I would like to have a hands-on like experience in this course, and that is why I'm a part of this course.
Thank you.
Hi everyone, this is Shekhar. So my personal interest would be I'm a bit passionate about singing and writing poems and stuff. And yeah, that's it. And I'm actually a bit good in software, not that good in hardware. So that's the reason why I'm here. I want to learn more in hardware. So
Great, thanks.
Hi guys, I'm Sanjana, and my personal interest, like I like to dance and I love traveling. I want to make a lot of memories traveling, and I think I'm better in software than hardware. That's because I've not done a lot of hardware, and my specific goals for the course, I want to make my fundamentals strong. I want to improve like how I tackle problems. Yeah, that's all.
Thank you. And the next row.
Hi, my name is Raza. My personal interest would be I like playing soccer and doing cycling and research and hanging out with my friends, best friends. And my strength, I would say, is mainly in hardware because of the course I've taken and the projects I've done. My specific goal of the course would be doing a project from like the bottom-up approach, like starting from scratch and doing from understanding embedded systems from like the registry level, which I haven't done much. So yeah.
Thank you.
Hello everyone, my name is Shashidhar. I'm from Bangalore, India. My personal interests are quite varied. I love traveling, I love cycling, I love music, I love playing music, and yeah, but I haven't really had the time to follow them like after coming here, but yeah, I'd love to do that. And my strength in hardware or software, I would say I haven't really explored hardware much, so I would say software is something that I know and I feel I'm a little stronger there. And specific goals for the course, I would say to learn to implement. So my background is a bit of signal processing and embedded systems. So my specific goal for the course is trying to understand implementation of DSP algorithms on an embedded chip. So that's what I'm looking for, and hopefully it will turn out good. Thank you so much.
Thank you.
hi, I'm Avinash. I'm also from Bangalore. My personal interests would be traveling, and I like cooking as well. It's an offbeat. I'm better at software than hardware because I've lost touch with hardware. So that is why I'm in this course, to get to the basics and then to know all the nuances of building an embedded system. And that is why I'm in this course, and I hope I learn.
Great. Thank you.
Hi everyone, my name is Ji. I'm a September student and I'm from China. My personal interests are cooking and traveling and reading, and I'm stronger in software. So I'm here want to improve my hardware and to improve the power electronics about circuit.
Great. Thank you.
Hi
Next row
everyone.
back.
I'm Sandeep Raj. So my personal interests were like watching movies a lot and reading Wikipedia pages of stuff that I really wanted to know about, like aliens and stuff. And I used to listen to a lot of music and watch a lot of movies before, but after coming here, that yeah. So I'm good with writing firmware because I learned how to write good firmware, like or low energy firmware, in my first sem. But I don't have good hardware knowledge, so that's the reason I took this course. Yeah, and after coming to Boulder and seeing the beautiful mountains around, I learned to learn a lot of patience in hiking and trekking, and also a lot of interest in doing such stuff.
Great. Thank you.
Hi everyone, I'm Shreyas. Coming to my personal interests, I would say playing soccer, playing video games, and I love watching documentaries. One of my favorite shows is air crash investigation. Like I have a lot of interest in aeronautics as well, and comparatively, I feel I'm strong in software because I have not done any courses in hardware, and that is one of the reasons I took this course. And coming to the specific goals for this course, I would say making my fundamentals stronger and also improving my knowledge in hardware.
Thank you.
Hello everyone, I am Dharmik. My personal interests include music, movies, and hanging out with friends and enjoying with family. I am stronger in software, and my specific goals for the course are I want to strengthen my fundamentals and I want to build a robust embedded product.
Great. Thank you.
Hi everyone, I'm Lakhan, and my personal interests are cycling, playing chess, caroms, and astronomy. And yeah, I do a lot of things. And also, I'm stronger in software compared to hardware. I'm better off developing software. But then I want to like really design something, some cool project out of this course and like embedded system, which I'll feel good about it later on. So that's why I'm taking this course.
Hi everybody, I'm Ria. I'm from Mumbai. I love reading, I love traveling, I love music. I wish I could play some. Well, I've dealt more with software, and in the last semester itself, I realized how some of the problems that I was facing were because I didn't know a lot of hardware concepts. So I'm hoping I get that out of this course. I get to strengthen that part, and hopefully write better software for my projects.
Thank you.
Hi, my name is Farah, and I'm interested in reading, writing, hiking, and writing. And all of those things I've done before, but I've gotten out of touch with them while I was working. So I'm getting back in touch with them, and especially because Boulder is so famous for hiking and writing both. I personally feel that I'm good in software, obviously because I've worked more in that, but I have been working in operating systems and architecture, so I do have an idea of hardware, just that I've never implemented those ideas, and that is why I am in this course. And specifically, I'm hoping that my PhD research can be connected with this course in some ways where I can understand the working of sensors and how they work in my embedded design that I eventually would be able to use in my project.
Great, thank you very much. Well, that was very interesting. Thanks for sharing a little bit. It's great to get to know a little bit more about you, and hopefully we'll have some more opportunities as we go through the semester to interact like that. We've reached the end of our time period. If you haven't signed the attendance sheet, please do so. That'll be collected and by the operator. If you have not yet picked up a parts kit or toolkit from the TA, you can do that. Hopefully you saw the announcements before, but it's time to get that hardware and get your software portion of Lab 1 done so that you can get started immediately on the hardware. And then if you have not done soldering or wire wrapping before, take advantage of the tutorials or training sessions that the TAs offer so that you really develop that skill well now, because you want to do a really good job as you go through the semester. And if you start with some poor solder joints or poor wire wrappings, those could continue to come back and hurt you in your debugging phases later on. So better to get it all practiced and really good shape right now. And then as you're thinking about final projects, I am looking for real engineering content in your final project. And so some people have asked, well, could I just use Arduino or something that's more canned, something I just choose and all the hard work is done behind the scenes for me? That's not what I'm looking for in this course. You're really learning good skills and fundamentals in this course. I want you to show me that in your final project. So if you're going to use you know, a specific set of hardware that's already pre-done, you want to add in hardware that you're doing yourself as part of your final project. And I want you to start thinking that way as you figure out what you want to focus on. You've still got many weeks before we have to do our PDR, but I want to set the expectation that you need new engineering content in both hardware and software for your final project. With that, are there any questions before we wrap up tonight? All right. Well, I'll hang out here just for a couple minutes while you're getting ready to leave in case you have other questions. But please get your Lab 1 sign-off for your software done. I am a little bit lenient on the timing for Lab 1, but you should get used to what I'm expecting so that we have a really smooth process through Labs 2, 3, and 4. Thank you all.
Thank you.
Professor,
Yes.
when are the training sessions held, like for the wire wrapping?
The TAs will send out an email on that. They told me that they've already made some videos and they're editing those, and then they'll communicate that. I'm expecting that to come out in the next day or two, but I'm not sure. You can always contact the TAs and ask the question as well.
You can pay for the using a PayPal or something.